In this lesson, you will identify and graph step functions and identify and graph absolute value and piecewise define functions. All three of these functions have a certain look to them, so here's a few vocabulary words just to help us. A step function is a function with a graph that is a series of horizontal line segments. Remember that mathematicians are not creative. It actually looks like steps as they're going up and up and up and up and up, or going down. A piecewise linear function is a function written to use two or more linear expressions, and so you're going to have one expression that's graphed, another on the same grid. So they might be two rays, they might be two lines. It just kind of depends on what the two expressions are. A greatest integer function is a step function written in this form, f of x equals, and it's a double bracket, x. That means f of x is the greatest integer less than or equal to x. The greatest integer that's going to be less than or equal to this value. And this is the first example that we'll do, so I'll show you what that means. An absolute value function is a function written in this form, f of x is equal to absolute value of x, in which the f of x has to be greater than or equal to 0. Remember, absolute value can never be negative, and so this would be for our values of x. And a piecewise defined function is a function that is written using two or more expressions. And I'll show you an example of what all of these look like. So let's start with the greatest integer function. Now, you know it's a greatest integer function because it has that double bracket. So when you are finding your x and y values, what might be good is to have another category here, and you're going to maybe have to have a double bracket just to remind you that it's got to be the greatest integer that's less than or equal to that value of x. So another name for y here would be f of x in this case. So when I start with, let's just start with 0. If I start with 0, this is going to be 0 plus 2, which is 2. Well, the smallest, or the greatest integer that is less than or equal to 2, obviously, is 2. So then we might want to try something maybe fractional. So let's do 1/4. 1/4 plus 2 is 2 1/4. Well, what's the greatest integer that's less than or equal to 2 1/4? Remember, integers have to be whole. Well, it would be 2 again, right? So then we have a half. Well, that would be 2 1/2. Greatest integer that's less than or equal to would be 2 again. How about 3/4? That would be 2 3/4. The greatest integer that would be less than or equal to this is 2 once again. You're not going to hit 3 in this category until you hit 1 here. 1 plus 2 is 3, and now everything that's bigger than 1 would be 3. And what we've created are these barriers. So when I graph, I know that it's going to stay at 2 until I get to the next whole number. So if we say that this is 0, right here, this is 1, this is 2, it's going to be kind of hard to see what's going on with the graph. So what I'm going to do is I'm going to have this be 1 and this be 2 just so we can see what's going on. And this is 3 and so on. So I'm going to just widen my graph just a little bit by whole numbers just so we can really see what's going on here. So at 0, it is going to be 2. And then at 1/4, it's 2. And it's going to be 2 all the way to 1, where then it jumps up to 3. So when I have a solid dot on the 3, I have to have an open circle here because it's not equal to 3. But I have my segment going all the way in front. So what's going to happen with the 3? Well, it's going to be 3 all the way until I get to the next one, which would be, in this case, 4. And that would be all the way till I get to the next one, which is 5. And do you see how it looks like steps? This is what we call a step function, where I have that step pattern. When you graph something that's a greatest integer function, it's always going to look in a stair-step pattern. So you try the example in your notes. Now, another example of a step function, a cell phone company charges by the minute, not by the second. So if 45 cents a minute or any fraction thereof, exceeding the number of minutes on the plan. So let's have our X values be our number of minutes and our Y values are going to be how much money. So you can talk for anything between 0 and 1 minute and they're going to charge you 45 cents. And they're not going to charge you 90 cents until you've gone over that minute. So anything from 1 minute to 2. And then from 2 to 3 would be $1.35. And from 3 to 4 would be $1.80. So this is going to be definitely a stair-step pattern. And when you are looking at your graph, if I have anything from 0 to 1, let's just count by 45 here. Let's say this is 45 cents. Anything from 0 to 1 whole is going to be at 45. And then I'm going to circle at 1. Because 1 minute, once I hit that minute, or no, I would have a dot, solid dot at 1. Sorry about that. If I don't call it all, it would be 0. So then here's my 90 cents. And I'm going to go anywhere between, they charge me here. So at 1 minute exactly, it's going to be an open circle. And then to 2 minutes, at 2 minutes, I still be charged 90 cents. And then $1.35 is next up, and that's anywhere from that 2 minutes to the 3. And now I've created now a stair-step pattern, just like we had in the last example. And you can continue on and graph. Now, in this step pattern, what we should talk about is our domain and our range, because those are something you would have to identify. Our domain, we could have any values of X, but in this situation, we can't have negative minutes. We can't go backwards in time. So our domain has to be all positive X values. And that could be, we can have fractions of a minute, we can have fractions, so that's okay. It can be any value, but it has to be positive. Our range, if you'll notice here, our range is going to be obviously never negative, it'll be always positive. And we're always going to be counting by those 45s, because it's 45 cents, 90 cents, and it's always going to be counting up by 45s. And so we have some fractions in here, we have some decimals. So we could say all positive reals here as well, because that is going to be never negative. So you can identify domain and range of any graph that you draw. So let's move on and talk about an absolute value function. In an absolute value function, you are going to always see a positive result because an absolute value can never be negative. So let's just start with -3. We'll try -2, -1, 0, 1, 2, and 3 just to see what's going on with this graph. So -3 minus 4 is -7. Well, how far is -7 from 0? That's +7 spots. -2 would be +6. -1 would be +5. 0 would be +4. 1 would be +3. 2 would be +2. 3 would be +1. Now at 4, it's going to be exactly 0, because 4 minus 4 is 0. At 5, it's 5 minus 4, which is 1. And as you're going to see, then at 6 it would be 2, and so far it would be all those same values. So what your graph would look like at -3, here's 7, -2 is 6, -1 is 5. You're going to see these rays. 1 is 3. And what's going to happen is they'll go back up. An absolute value always looks like a V, always. Every absolute value function will have this same V shape. So you'll notice then that there are 2 rays and they form that V. The domain could be any value of X. You could do fractions, so it would just be all real numbers. And you could plug in negatives as well. But our range, as you can see, is going to be any value that is greater than or equal to 0. You're never going to see negative values in an absolute value function. So try